Well, welcome back to another exciting night. Tonight's focus is on sequences. Now, you talked about sequences and series back in Algebra 1, so hopefully tonight will be a little review and then we'll get into some more deeper mathematical concepts. So just to recall, a sequence is an ordered list of numbers. For example, 2, 4, 6, 8, etc. And really what we're saying is f of 1 is 2. So the first term is 2, f of 2 gets me 4, f of 3 is 6, and going on. So let's dive into our first question. A sequence is defined by the equation a sub n equals 3n minus 1. So notice how I read that. This is not called an. This n is a subscript, so we call it a sub n. Perhaps you want to write that down in your notebook for yourself so you speak mathematics correctly as well as do the math correctly. A sub n equals 3n minus 1. Question A says find the first three terms of this sequence. So if I want to find the first three terms, I really want to find a sub 1, a sub 2, and a sub 3. And again, the 1, 2, and 3 are implying first term, second term, third term. So it's very simple. I'm going to start with the formula a sub n equals 3n minus 1. And I'm simply going to replace all the n's with the number 1. Okay, so this becomes a sub 1. I'm replacing all the n's with a 1. 3 times 1 minus 1. 3 times 1 is 3 minus 1 equals 2. So a sub 1 equals 2, and all that's saying is that the first term is the number 2. Now notice they wanted the first three terms, so we're going to keep going. I'm going to need to find a sub 2. So I'm going to replace in my original formula here all the n's with the number 2. So 3 times 2 minus 1, that's 6 minus 1, which is 5. And then I'll go get the third term, a sub 3. Again, I'm just replacing all the n's with the number 3. So 3 times 3 minus 1, that's 9 minus 1, which is 8. So my first three terms are a sub 1 is 2, a sub 2 is 5, and a sub 3 is 8. So I would say I have 2, 5, and 8, and I could go on and find as many as I want. The question just said what are the first three terms. The second part to the question says which term will have a value of 80. So the question is now basically what is the value of n? What term will give me a value of 80? So basically I want to say 80 equals 3n minus 1. And I'm going to solve for n. So I'll add that 1 over, so 81 is equal to 3n. I'm going to divide both sides by 3. And hopefully we get n equals 27. Okay. Our next big definition is the word recursive. So sequences can also be defined by recursive definition. So let's kind of box that in or underline it, highlight it for yourself. When a sequence is defined recursively, its terms are found by using previous terms. So let's take a look at a recursively defined sequence. Question 2. A sequence is defined recursively. F of n equals f of n minus 1 plus 2, and f of 1 equals negative 3. So the question A says find the first 5 terms. So here's how we're going to set up these recursive ones. Okay, we're going to draw 2 lines here, and we're going to highlight these very clearly for ourselves. The variable in the problem, so in this case it's an n, is going to be what goes in this column. The rule will go here. So my rule is f of n equals f of n minus 1 plus 2. And then basically my answer is going to go in that third column. So it says find the first 5 terms. Well, it gave me 1 to start with. They said f of 1 equals negative 3. So when n is 1, I don't need to plug it in because they're telling me the answer is negative 3. Okay, so there's the first term. It's done for us. That's what recursive means. We're going to use a previous term. So let's go ahead and get n equals 2. So again, the rule just says you're going to replace all the letter n's with the number 2. So I'm going to say f of 2 equals f of 2 minus 1 plus 2. Okay, now, the more steps you show on your cleanup, the easier this is. F of 2 equals f of 2 minus 1, which is really f of 1 plus 2. And here's where the recursive part comes in. You're going to use the previous value of f of 1. F of 1, we already know, is the number -3. So this is actually -3 plus 2, and I get an answer of -1. All right, and we just continue, we do this again. So now I want to find f of 3. I want the third term. So I'm going to substitute a 3 into n, and I'm going to carefully replace all the n's with a 3. So f of 3 equals f of 3 minus 1 plus 2. Simplify that math. F of 3 minus 1 is actually just the number 2 plus 2. And f of 2 recursively is the previous term. F of 2 is right there. So that becomes -1 plus 2, which is equal to 1. Okay, so again, the more steps you show, the easier this is. Now, one of the first 5 terms, so I'm going to keep chugging here. Now I'm going to need when n equals 4. So f of 4 equals f of 4 minus 1 plus 2, which is really f of 3 plus 2. And f of 3 is this previous term of 1, so I get 1 plus 2, which is actually just 3. And we'll go one more to get that fifth term. So I'm going to say that's f of 5 equals f of 5 minus 1 plus 2. 5 minus 1 is actually just f of 4 plus 2. F of 4 is that previous term, so that's just 3 plus 2, which is 5. Okay, so there you have it. We have this recursively defined sequence that we just get by using the previous term. So if I were to list the sequence out, let's see, it went with -1, then 1. Did I miss a term? I'm sorry, it started with -3, then -1, then 1, then +3, then +5. So there's the first 5 terms I have in the sequence. Let's try another recursively defined one. Question 3. For the recursively defined sequence, excuse me, find t sub 5. Now remember, every time this is a small subscript, make sure you say sub. So this is t sub 5. And here's the formula. T sub n equals t sub n minus 1 squared minus t sub n minus 1. And they were given t sub 1 equals -2. So again, you know it's recursive when they give you a term to use. That's the recursive part. So it's pretty straightforward. I can't get to t sub 5 without 1, 2, 3, and 4. So I just have to slow down and set my problem up. So again, I'm going to draw on these lines. The variable in the problem is what's going to go here. And again, in this case, it's t sub n, so my n is my variable. My rule is t sub n equals t sub n minus 1 squared minus t sub n minus 1. All right, now again, we know the first term, they gave it to us, so when n is 1, I know the answer is -2. Now I just go in order, so now I need n to be 2. And I'm just going to carefully plug it in. So t sub 2 equals t sub 2 minus 1 squared minus t sub 2 minus 1. And again, clean it up. This is t sub 2 minus 1 is really just t sub 1 squared minus t sub 1. And again, I'm just saying 2 minus 1 is 1. So I'm just going to keep cleaning that up. T sub 1, again, is right here. So this becomes -2 squared minus t sub 1, so minus a -2. -2 squared is a +4, and minus a negative actually turns into a +2, so I get an answer of 6 for that second term. Okay, now remember, you needed the fifth term, so we're just going to keep going. So if I want the fifth term, I got to get the third, so carefully replace that. So t sub 3 equals t sub 3 minus 1 squared minus t sub 3 minus 1. Okay, so let's see, t sub 3 is equal to now, this becomes t sub 3 minus 1 is 2. squared minus t sub 2. T sub 2, if I look back, is 6. So this becomes 6 squared minus 6. So that's really 36 minus 6 is 30, and there is the third term. And again, my goal is to get to the fifth, so I'm just going to keep chugging here. I have to get the fourth term. So t sub 4 equals t sub 4 minus 1 squared minus t sub 4 minus 1. So this really becomes t sub 3 squared minus t sub 3. Okay, so I'm going to go back. T sub 3 we know is 30. So this becomes 30 squared minus 30. Well, 3 squared is 9, and I'm going to add 2 zeros on to get 900 minus 30 is going to get me 870. So this number is getting pretty big in a hurry. So the fifth term, let's get her set up there. I'm going to say t sub 5 is equal to t sub 5 minus 1 squared minus t sub 5 minus 1, which is really t sub 4 squared minus t sub 4. And I'm going to have to grab my calculator to do that. But anyways, I'm taking t sub 4, which is 870. I have to square that and subtract 870. And I'm going to let you grab your calculator and get that number. I don't have mine handy. But that would get me my fifth term. So again, all a recursive sequence is you're using the previous term to get the other one. And really, the more steps you show here, the easier it is to get that answer. Question 4. Determine a recursive definition for the following sequence. 5, 10, 20, 40, 80, 160, etc. So the first thing I do is I have to figure out the pattern. Sometimes it's really obvious and sometimes it's not. I'm hoping this is a pretty friendly one. How am I getting from 5 to 10 to 20 to 40 to 80 to 160? What do you notice is happening each time to these numbers? Hopefully right away your gut's saying, oh, this is nice. I'm just simply multiplying the previous term by 2. Would you agree 5 times 2 is 10, times 2 is 20, times 2 is 40, times 2 is 80, times 2 is 160? And as long as it works for everyone, you know you've got the right pattern. So I actually want you to write that out in words. We're saying each term is multiplied by 2. Okay, so I'm taking 2 times the previous term basically. So once I know that, I can write the rule. Now notice it says recursive, so you're going to have to give a formula and then you also give the first term. So I'm going to say f of n, and you can call it a of n, call it whatever you want. I'm going to use f of n for function, is equal to 2 times. Now basically in words, would you agree you want the previous term? Right? It's 2 times the term before it. So 10 is 2 times the previous number. 20 is 2 times the previous number. Well, the previous number is just the number in front of n. So I'm going to say f of n is equal to 2 times f of n minus 1. If n is the number I want, the previous term is the number before it. So n minus 1. Now, you would almost be done, except again it said recursive, so box this in. You also need to give the first term. And if you just look, the first term is 5. So f of 1 is equal to 5. Okay, so now I have a recursive definition where I'm given the function and the first term. And you could quickly go through, you could do a couple examples just to prove that you're right. So I'm going to do that real quick just to prove it. If I say n is equal to 1, I should get out a 5. If I say n is equal to 2, I'm just going to carefully substitute in a 2. So that's 2 times f of 2 minus 1, which is really 2 times f of 1. F of 1 is 5 times 2 is 10. So I can see that the first two numbers worked out. And you could keep proving that your sentence is actually true. Okay, but again, let me go back here. I just said I needed 2 times the previous term, so that's 2 times f of n minus 1, and then I'm going to list that first term out. So one of the most famous sequences in mathematics is called the Fibonacci sequence, and this can be related to all sorts of things, whether it turns into math, to music. This is a really famous sequence. So this sequence is defined recursively using 2 previous terms. So we've only done some recursive sequences with one previous term, but now we're going to be given two. So go ahead and copy this down. F of n equals f of n minus 1 plus f of n minus 2. And we're given two previous terms, f of 1 equals 1 and f of 2 equals 1. Find the next four terms. So they gave us terms 1 and 2. They say the next four, so we have to find four more terms. So I'm going to make that same table that I made before. Okay. Again, the variable in the problem is n, so I'm just going to call this n. I'm going to put my rule here. F of n equals f of n minus 1 plus f of n minus 2. So they're giving me two rules. They're saying when you plug 1 into n, you get 1 as an answer. And when you plug 2 into n, you get 1 as an answer. So now my goal is to get the next four, so I'm going to plug in the number 3. So again, just write it real carefully. F of 3 equals f of 3 minus 1 plus f of 3 minus 2. Now notice how it uses two previous terms, because now I end up with really f of 2 plus f of 1. And let's see, I know f of 2 is equal to 1, and I know f of 1 is equal to 1. Where am I getting that from? Right here. F of 1 is 1, f of 2 is 1. So I know that this third term is actually equal to 1 plus 1, which is 2. I'm just going to kind of break this up a little bit. So now I have the first three terms. All right, let's go for the next one. If I plug in a 4, so I'm going to get f of 4 is equal to f of 4 minus 1 plus f of 4 minus 2. So that's f of 3 plus f of 2. So now I need the third term, which is a 2, plus f of 2, which is a 1, and I'll get an answer of 3. Okay, keep going here. So now I need 5, so to the next four terms. So let's see, f of 5 is going to be equal to f of 5 minus 1 plus f of 5 minus 2. So that's f of 4 plus f of 3. F of 4 we said is 3, f of 2 is 2, so the fifth term is 5. And we'll go get one more here. 6, let's see, so f of 6 is equal to f of 6 minus 1 plus f of 6 minus 2. So that's f of 5 plus f of 4. So that's going to get me 5 plus 3, which is 8. So now here's the really cool thing about the Fibonacci sequence. Let's go ahead and write them out. I had 1, 1, 2, 3, 5, 8. So go ahead and write this out with me. 1, 1, 2, 3, 5, 8. Do you see the pattern? And again, this is a famous sequence. There's so much on the web. You can research all this, the web. You can take classes and books all about just this sequence and how it comes into math and musical studies. 1, 1, 2, 3, 5. Could you predict what the next term is? So let's recall that rule. It said basically you're taking the first two terms and adding them together. So check this out. 1 plus 1 got you 2. Okay, so now this term should be the sum of the two previous terms. 1 plus 2 is equal to 3. So this term should be the sum of the two previous terms. 2 plus 3 equals 5. This term should be the sum of the two previous terms. 3 plus 5 should get me 8. Let's keep going. The Fibonacci sequence basically says just add the two previous terms together. 5 plus 8 tells me the next term should be 13. The next term should be the sum of the two previous terms. 13 plus 8 is 21. And again, this can go on and on forever. It never ends. It's a sequence. It's just the sum of the first two previous terms. Again known as the Fibonacci sequence. So again, here's our Fibonacci sequence, or the sum of the two previous terms. And like I said, this is naturally occurring in nature, in the shape of shells, in all sorts of things. And feel free to, look into it a little more yourself here. But it does create, if you draw it out a specific way, this thing called a golden spiral, this Fibonacci sequence. And basically what they do is they start with rectangles a certain size. So remember the sequence went 1, 1, 2, 3. They make a rectangle 1 by 1 and another one 1 by 1. And then off of that, the two ones together can make a 2 by 2. And then a 2 and a 1 can total a box of 3. And a 3 and a 2 can make a box of 5 on the end. And then you'll notice 8. And you can keep going in this pattern. And if you start at the ones there, and you kind of go from corner to corner diagonal, and then back up to this diagonal, and then to that diagonal, and then to that diagonal, and this diagonal, and then back to this diagonal. And now you can create the 8 plus 5. You can make another rectangle based off here, and it just keeps going around, and it creates this naturally occurring golden spiral. All right, find an algebraic formula for each of the following sequences. So let's go ahead and underline or circle that algebraic formula. Notice it doesn't say recursive this time. So we don't need a previous term. We just need to come up with a rule for the sequence. So here's how I attack it. I'm basically looking for the pattern that goes 4, 5, 6, 7, etc. This can go on. So I'm saying when I plug a 1 in, when I let n equals 1, I have to get a 4. So I make a little key for myself. 1 has to turn to 4. When I plug in a 2, I have to get a 5. So 2 has to turn to 5. When I plug in a 3, I need to get a 6. And when I plug in a 4, I need to get a 7. So how does that happen? How do I go from 1 to 4 with the same idea, 2 to 5, 3 to 6, 4 to 7? Some of these are super easy to come up with and some are a little tougher. I think this falls under the easy category. Wouldn't you just say you're adding the number 3? 1 plus 3 is 4, 2 plus 3 is 5, 3 plus 3 is 6, 4 plus 3 is 7. So I got the pattern. Let's just write the rule. A sub n equals n plus 3. Right? We said we're going to add 3 each time, so I'm just going to say that's my n value plus 3. And you can test it. If I plug in a 1, I get 1 plus 3, which is 4. If I plug in a 2, I get 2 plus 3, which is 5, etc. And you can test your theory out. Let's go ahead and try another one. Let's say we've got 2, 4, 8, 16, ... So this goes on forever. Again, I want to write an algebraic rule. So I'm saying when I plug in my first term, I need to get out the number 2. My second term needs to turn into a 4, my third term to an 8, my fourth term to a 16. So again, some are easier to see than others, and that's okay. We just gotta, get creative here. So think about it. How does a 1 go to a 2 go to a 4, a 3 go to an 8, a 4 to a 16? Well, again, I'm going to say my rule is a sub n equals. All right, so these numbers do stick out to me. I'm saying this is 2 to the first, this is 2 to the second, this is 2 to the third, and this is 2 to the fourth. So I'm going to call my rule 2 to the n. 2 to the first is 2, 2 squared is 4, 2 cubed is 8, 2 to the fourth 16, etc. All right, here's another sequence. 7, 7 halves, 7 thirds, 7 fourths. So again, I'm saying when I plug in a 1, I want a 7. When I plug in a 2, I want a 7 halves. A 3, I want a 7 thirds. 4, I want a 7 fourths, and this pattern has to continue. So I think there's one fairly nice thing about this is notice the numerator is always the number 7. And technically you can consider that as 7 over 1. And looks like the denominator is just the value of n. So this is a really simple one. I would just say a sub 1 equals 7 divided by n. So the first term, a sub 1, should be 7 over 1, which is 7. A sub 2 would be 7 over 2. A sub 3 would be 7 over 3, etc. All right, letter D. Negative 1, 1, negative 1, 1. Obviously that pattern is going to continue, negative 1, 1, etc. So again, I just make a little note for myself. When I plug in a 1, I want to get a -1. When I plug in a 2, I want to get a 1. 3, a -1, and 4, a +1. So right off the bat, the only way I can keep getting 1 as an answer is I would have to have 1 to a power. So I'm going to say a sub n equals -1, and -1 to the first would get me a -1. So I'm going to call that n. -1 squared would get me a +1. -1 cubed would get me a -1. -1 to the fourth would get me a +1. Okay, so sometimes it's a little trial and error and just use a little common sense. Alright, our last one here to get creative on is 10, 15, 20, 25. So again, when I plug in a 1, I need a 10, a 2, I need a 15, a 3, a 20, and a 4, a 25. So right off the bat, I think the pattern that we see between these going this way is that I'm adding the number 5 each time. Okay, so I know I'm probably going to have something plus 5. Okay, but now think about this. When you plug in a 1, you have to get a 10. So what would I want to have here plus 5 that's going to get me a 10? When I plug in a 2, I have to get a 15. So again, let's just talk it out. If I just put n here, that would mean 1 plus 5 has to be 10. Well, that clearly doesn't work. I have to plug a 1 in and do something and add 5 to get that 10. What if I say 5n? 5 times 1 is 5 plus 5 is 10. If I plug in a 2, 5 times 2 is 10 plus 5 is 15. If I plug in a 3, 5 times 3 is 15 plus 5 is 20. If I plug in a 4, I get 20 plus 5. So there's my rule, a sub n equals 5n plus 5. Well, that does it for us tonight. An intro to sequences, and we look forward to some good practice.